In this next lecture series, we're going to talk about volcanoes. We're going to talk about them for a number of reasons. One, these volcanoes are a window through which we can see the interior of the Earth. They provide a conduit for materials to rise from within the Earth to the Earth's surface and even above the Earth. And this material provides us with the chemistry and the history, the thermal history, in some cases, of that material prior to it being exhumed. Volcanoes help us to understand plate tectonics and mantle convection. They provide a superficial depiction of what's going on below the Earth's surface. And volcanoes are importantly connected to the Earth's hydrosphere and atmosphere. This brings it into the climate system of the Earth as well, and that affects us on a very personal level. It affects our ecosystems as well. Now, this lecture is going to consist of a series of components. We'll start out with volcanoes as geosystems. We'll talk about lavas and other volcanic deposits, eruptive styles and landforms, the shape of a volcano, interactions of volcanoes with other geosystems, the global pattern of volcanism. Volcanoes aren't distributed randomly on the Earth's surface. It's the position of them around the Earth that tells us something about what's going on within the Earth. And lastly, we'll talk about volcanism and human affairs, how volcanoes directly affect human history and how they may directly affect our future. When we talk about volcanoes as geosystems, we're talking about parts of a volcano. These components include a hill or mountain made up of lavas that include other materials such as ash and mud. The parts of this geosystem include the rocks themselves that make up the volcano, the magmas and lavas that ultimately generate the rocks, and the process of melting and eruption, how those magmas become magmas, and how those lavas become lavas, and how they're distributed above the geosystem, the volcanic geosystem in this case. When we look at this geosystem, this is an important diagram to get a handle on, as it illustrates in general terms what's going on in most, if not all, volcanoes. Starting down low in the asthenosphere, the weak sphere of partial melting, magma is going to originate. And because of its lower density, partially due to its heat, partially due to its chemistry, it's going to rise like a lava lamp, a blob of paraffin in a lava lamp. It's going to rise through this crust, again because it's more buoyant, and displace that crust. Ultimately, it may accumulate as a magma chamber. This magma chamber itself can release material intrusively as sills and dikes. Again, sills are concordant with previous structures, dikes are discordant with previous structures. Or this magma can rise to erupt as a central vent, the main cone or eruptive crater of the volcano, or it can come out of the side. This happened catastrophically in the case of Mount St. Helens. Mount St. Helens erupted sideways instead of vertically, and that surprised a lot of people that were killed in particular. Now, once this material is ejected, it can accumulate on the surface, and this accumulation of material at the surface can become a volcano. So what we see here is, again, a central pipe or a central vent, a side vent here. Each of these can release lava or ash and, of course, gases as well. And that may flow down the side of the slope, or it may be mixed with layers of lava, layers of ash, layers of lava, layers of ash, and kind of a composite cone. When we talk about volcanoes as geosystems, we talk about the function of the geosystem itself. This includes its plumbing, as we saw in the previous diagram, and it includes its ability to change chemistry. It serves as a chemical factory. It takes maybe one magma and mixes it with another magma, or it takes a magma and mixes it with dissolved country rock, adds some gases, adds some fluids, and you get a chemical factory that's going to emit some product. The types of lava that are emitted from volcanoes include basaltic lavas. These are hot, very fluid, quiescent, that means they're not explosive, and they're massive. They can be very, very large flows. A'a is a jagged form of volcanic rock, whereas Pahoehoe is a ropey-looking type of volcanic rock. And then we have pillow lava. These are very common in places like mid-ocean ridges. They can form in lakes, they can form in rivers, they can form in oceans, wherever lava comes in contact with water. And here's a convenient picture that shows both A'a and Pahoehoe. Easiest way to remember this is if you walk on this A'a, it shreds your shoes. You'd say, ah, it tears through your feet. It will literally destroy your shoes after a few hours of walking on this stuff. Pahoehoe is generated by more of a fluid flow, and you can see that, kind of a taffy-looking appearance, or ropey. This is where that type of lava forms. This is Kilauea in, I believe, 2010. So there's an active eruption here, and the lava is flowing directly into the Pacific Ocean. And you can see that again here. What is above in this cloud is a mixture of CO2, H2S, and water vapor. Very, very hot and toxic. If you try to get closer, you'll see these signs. Area closed due to volcanic gas. Stay in your car. I don't know if they put this over this because they realize that it doesn't matter if you're in your car or not, if you're in a cloud of poisonous gas, or they just thought it was overreach, or somebody's angry about their freedom. Anyway, if you're in a car in a cloud of dangerous gas, that's the wrong place to be. Here we see some pillow lavas on the floor of the Pacific Ocean. These can be thought of as being generated when the lava comes out of a lava tube, like toothpaste coming out of a toothpaste tube. You get these shapes, and we can recognize these in ancient rocks, very, very old rocks. We can still see evidence of these pillows. If you go to Flin Flon, which is in Manitoba, to do your field school up there, you'll see lots of pillow basalts, but very, very old pillow basalts. This is a lava tube in Volcanoes National Park in Hawaii. It formerly was a conduit for magma. So the magma would flow through this tube, which is inappropriately called a lava tube. So it's more of a magma tube. It flows until it reaches the air or the water, where it's going to harden. If it hardens in the water, it forms a pillow. If it hardens in the air, A'a or Pahoehoe, most likely. And here we have an image, sort of an air photo, Google satellite photo of a couple of the Hawaiian islands. And we'll talk about Molokai here. So Molokai, you'll notice, is not shaped like any other Hawaiian island. The other Hawaiian islands are all more or less volcano shaped, roughly equant. This is shaped like a strange shoe or a zucchini. And you'll notice, perhaps, there's some kind of debris here on the sea floor. And what this debris is the other half of Molokai. So Molokai used to be about this size, at least superficially. This broke off and then fell into the Pacific Ocean, generating a very, very large tsunami. We don't have any historic record of that. It happened quite a while ago, but there was definitely a very large tsunami. And today, if you visit Molokai, you can go to Kalaulapapa Peninsula. This Kalaulapapa National Historic Park is dedicated to people that were shunned for having a disease known as leprosy. It's now known as Hansen's disease. It's only contagious to about 4% of the human population, so most people don't get it, but that wasn't known at the time. The transmission was assumed to be any kind of contact. Even if you saw somebody with leprosy, maybe you could get it. Of course, that's not true, but those are the rumors. The result was any Hawaiian that was suspected of having leprosy was dumped off in this place on the edge of this island, which is broken in half. And it looks like this today. The reason they were dumped off here is that nobody could climb up these cliffs. These are about 3,300 feet high. These cliffs are very high, very steep. It's very rugged terrain, and there's very little chance of escape. So once you're dumped here in Calulapapa, you're not going to get away. And unfortunately, people with leprosy or people that were thought to maybe have leprosy were dropped off here and cut off from all communication with their family and basically left to live out their lives here in isolation with other people suffering the same fate. View from 1905. This is Father Damien's church. Famous story of a Belgian priest named Father Damien who dedicated his life to helping the people that were stranded here in Calulapapa. He contracted the disease himself, and he's buried just on the other side of this church. Now, when we look at Hawaii, today the islands are here. The island of Hawaii, also known as the Big Island, is located right here. You'll notice there's a string of islands, almost a straight line of islands that have been weathered away, such that they are now seamounts. You'll notice this continues to this point, at which there's a turn and then another straight line sequence of seamounts that are much older. Going all the way up to the Kamchatka Peninsula of Russia, we can see that some of these rocks are around 93 to 120 million years of age. And ophiolite is a chunk of crust that gets pushed up on top of other crust, in this case ocean crust on top of continental crust, or at least island arc crust. So 100 million years ago, a hot spot moved from this location southeast, or south-southeast, to this point, where it then takes a sharp turn, generating the Hawaiian seamounts. And these range in age from a few tens of millions of years to today. Lava is pouring into the Pacific Ocean today, making up the newest part of the island of Hawaii. When I was over in Siberia the first time talking to the head of the Archaeological Institute in Novosibirsk, he invited me and this other scientist, Ezra Zubro, to come out here to Kamchatka to do some archaeological work. And I thought, well, yeah, that'd be cool. One of those giant pink Russian helicopters, the 12-bladed pink monsters that always crash. I thought that would be a cool way to see Kamchatka. And then something happened to my schedule and I didn't end up going. I don't remember. Someday, this is a really, really weird, really hard to get to, really cool place geologically and biologically. So seamount is a large geologic landform that rises from the ocean floor but does not reach the water's surface. Therefore, it's not called an island, an islet, or even a cliff rock. These seamounts usually form when extinct volcanoes rise from the seafloor and then get weathered away, chopped off. So they're oftentimes tree stump shaped. And we can see that these seamounts can be found throughout all ocean basins, really. And they can range in height from 1,000 to 4,000 meters. In the case of the Hawaiian Islands, if you count the distance, the height from the Pacific floor to the top of Mauna Loa or Mauna Kea, we're talking about the largest mountain on Earth. There's a greater distance between the top of Mauna Loa and the Pacific seafloor than there is from Mount Everest to sea level. Okay, one last look at the Hawaiian island chain from a slightly closer, slightly different perspective. When we look at the motion of the Pacific plate, it's generally north-northwest compared to the motion or position of the mantle plume that currently sits under Kilauea on the Big Island of Hawaii. As these islands age, erosion wears them down to sea level initially, then below sea level with maybe a coral atoll around them. Eventually they'll sink below the surface and become a seamount. As we move closer to the recent, the islands have had less time to wear down, therefore they tend to be larger. So we're on the Big Island here. It's the Big Island because it's the young island, it's the new island. Molokai cracked in half about 1 million years ago or so it was much reduced at that point. The debris field is pretty substantial off to the north, so different perspective here would be off to that side. Regardless, the longer an island sits, the more it gets worn down, the more likely it is to become a gaio. Now, returning to types of lavas and volcanic deposits, we're going to go into the cooler lavas. These are andesitic or intermediate, named after the Andes Mountains. Andesitic intermediate lavas erupt at less than 1,000 degrees centigrade. And this is in part because there's more silica present and because of the lower temperature and the increased silica, these lavas are much more viscous, sticky, goopy, glue-like, tar-like, more like that than the runny, thin basaltic flows that come out of places like Hawaii or Iceland. So this viscous material at this low temperature can actually plug up the volcanic vent, and that allows pressure to build until we end up with a very explosive eruption that we saw 41 years ago in Mount St. Helens. Rhyolitic lavas take this up a couple notches or down a couple notches in temperature. Erupting between 600 and 800 degrees centigrade, they generally have 70% or more silica. They're very viscous because of this increased silica and the lower temperature, and the result is the most violent eruptions of all, Yellowstone Park being the most spectacular, most recent North American mega eruption. Here's a picture of Mount St. Helens before it's about to go off. The eruption started about March 27th, 1980, and it got people pretty excited because here's a volcano that's going to go off right by a big city, Seattle, making it convenient for volcanologists to get there and to set up in advance. April, the mountain began to build up and bulge, and then finally on May 18th, it went off spectacularly, and surprisingly, it was a lateral eruption. Here you can see a photo taken about 10 years ago. The mountain is here. The top of it is obscured by clouds, but it's not actually much higher than this cloud base here. What you see all throughout this area, throughout this view, except for the wall here, is devastation. All of the trees, all of the plants and animals were wiped out for many, many miles in this direction. What was left behind was a mountain that was 1,300 feet lower with a side missing. Again, this is a lateral eruption, so there was a landslide that reduced pressure on one side of the mountain, and it blew out in this direction. Also coming out in this direction was a lot of hot mud. The glacier that sat on top of this volcano, as sits on top of all the Cascade volcanoes, was melted rapidly during the eruption, and that meltwater from the glacier, coupled with the ash, led to the lahar that we see here, a hot mud flow. Very, very destructive. 57 people were killed. Most of them were killed by the lahar. Some, like the geologist, who the visitor center is named after, were killed by the blast itself. Mount Lassen, you probably haven't heard of. It's in California. It looks very similar to Mount St. Helens, and that's because it erupted in a very similar way in 1915. This eruption took place on May 22nd, 1915. Nothing special about May in terms of eruptions, just a coincidence here. This photo was taken from about 50 miles away, a bunch of kilometers. Taken at Anderson, where today there's not much going on, probably even less going on in 1915. There's a Wiener Schnitzel restaurant there, not a very successful chain in the US, but they got one in Anderson. Moving south to the other end of the world, this is an eruption, a recent eruption in southern Chile. And what we can see here is the spectacular buildup of static electricity in this hot, dry cloud. So this ash, very hot ash, gets blasted in the atmosphere, and the movement of each ash particle relative to other ash particles generates a static electricity, which you see being discharged here, and even more spectacularly here. This type of effect is common in volcanic eruptions, probably occurring in all or almost all eruptions to some degree. Moving to Iceland, back up to the top of the world, what we can see here is basically a huge volcanic deposit. All of Iceland is basalt, all erupted from the mid-ocean ridge, which lies below it. So this is a superficial expression of the mid-ocean ridge in the Atlantic, or the mid-Atlantic ridge. Each of these white things here is a volcano. This is the Vatnajökull, which is the ice that sits on the Vatn volcano here in the southeast. Other major volcanoes here include Hekla and Snæfellsnes here. This is the shortest way to get to hell, according to legend. You can walk there starting at this point here. Reykjavik, capital, is located down here. Reykjavik means smoky bay. It's smoky not because of smoke, but because of volcanic steam coming from near the bay. Down in the south, we have a volcano that you probably didn't know about until recently, maybe until this very moment, which is the Eyjafjallajökull, or Eyjafjallajökull, meaning the island's mountain glacier. So this volcano erupted pretty surprisingly and spectacularly in May. Again, May. Coincidence. In 2010. And it was initially discovered by airline pilots who flew over the Atlantic at night. They didn't know about the eruption. They knew when they landed they couldn't see out of the front window of the plane because it was all sandblasted away by flying through this ash at a couple hundred kilometers an hour. It also removed the paint from the plane. So that led to the European equivalent of the FAA shutting down the airspace. And one of my friends who was working in Ghana and Africa at the time emailed me and said, "Good news, there's a big volcanic eruption and I get to stay in Ghana an extra 3 weeks. I don't have to go back to work in Syracuse." So he was pretty happy. When we talk about big bad eruptions, usually we're talking about what's called a phreatic eruption. This is an eruption that takes place when water comes into contact with magma and it flashes quickly to steam, increasing its volume by several orders of magnitude. The eruption of Krakatoa in August of 1883 was one of these eruptions. It produced the loudest sound in history, and this sound was heard in Perth, Australia, 4,800 kilometers away. Killed about 40,000 people instantaneously, and it led to spectacular sunsets around the world, such as this one that was recorded in the famous painting by Munch called The Scream. You've probably all seen this painting. You might not have known that the weird swirly colors in the sky were actually pretty realistic for the day. And this is what's left of Krakatoa. This was the former outline of the volcano and the island. This is baby Krakatoa here, Anak Krakatoa, which is building today. So like Mount St. Helens, this volcano is not done. It's going to go off again at some point. Yellowstone Park is going to go off again at some point as well. And it's going to be big. It's going to be a disaster.